get started. Okay. Do you guys recognize this? Yeah? Picture of faces, right? Well, I imported okay. If I pass through this image content with some kind of threshold, threshold is to say that uncertainty with respect to the acceptability. Okay, so it said this is a person, this is a person, this is a person. There's a water bottle and there's a dining table with probability of 0.5. So the reason I set it up to acceptance threshold is 0.25. So if the confidence is below 0.25, it's not going to list it. So the minimum confidence it has is this item here, which is handbag. Now, what's good about this algorithm is that not only does it analyze the picture, it crops the picture, and it also gives you what's called a coordinate picture. So if you want to do some kind of image extraction, you don't have to find out where it is. It makes a rectangle around. Yeah? So it's like I take this picture. First of all, the algorithm that looks through, this is what we call pre-trained algorithm. Remember last time we talked about a neural network, we have to specify the architecture, right? And train it. But if the problem is well studied, somebody has already built the appropriate architecture and has already trained it. So this is like a pre-trained model. Look at the picture, yeah, scan through the picture, and recognize objects. Now this is actually a very difficult problem because it's not recognizing a particular face, right? It's not trying to compare. It's not doing pattern math per se. It's not like I have to do a picture, right? And I digitize it, and then I scan the digitization. And this is what we would think of as pattern math. But this that's actually scanning the entire face, sorry, entire picture, and identifying individual object. Now, having identified individual object, then the algorithm will like make a little bracket about it. And there's something in here. Okay? That is all the class. And this is where the pre-trained object recognition function takes over and saying, oh, I put a bracket around it, this is a water bottle. I put a bracket around it, this is a cup. I put a bracket around it, this is a bird. Okay? And again, in this thing, it's not picking up that air running all the way back, right? It's not picking the air conditioner, right? It's too small, it's tiny, and it's not clear. It could be anything. But the minimum stuff is a purse. Well, man purse in this case. Okay? So we got this handbag. Okay? So, you know, boys carry bags now. So we have man purse or handbag. This is the coordinate within that picture. This is a person for some reason, not very sure. Oh, because she's in the back and it's quite blurred, right? Right? Dining table, bottle, person, blah, blah, blah. Okay. Now, this is an example of a finished application that you can basically download and use for object extraction. So I think there was a team, Wang, I think, yeah, that wants to extract picture from picture what's in the Facebook. Now, if you did this, but instead of doing it just like I did, you name this thing. You say my data or something is equal to this, something like that, right? Then you can reference it later, which means that you can say, okay, let's say my object equal to this, right? Now this, by the way, so now that you have this, you can say what's dimension my object. So it's going to give you 11 by 4, so 4 columns, right? So if I address it by I want the first picture. Let's say I want this picture. This is what? First column, third row, right? So this is going to be third, comma, 1. Oops. 1, 2, 3. Just a second. 11, 4. Cannot take this. I'm doing something wrong here. I think it's table. It's definitely a table, right? So that yeah, you can reference it later. Definitely, I can isolate individual. So I can run through for this picture. I have. I think for your project, you only want the second column, right? You want to say that this is a person, or you can actually count. You can do a count. Yeah. So your model can be even more fine-tuned. So instead of saying that there's a picture of a cat, you can say the picture of two cats. Because it's not going to be overlapping. So if you identify two cats, it's going to be cat. Right? So you just count cats. Yeah. And again, set some kind of minimum threshold so it doesn't just pick up anything randomly. So this is an example of a case where the problem is well defined, right? You are applying to a new situation, but you don't need to replace anything because in real life, this kind of looking at the picture and trying to find what it is, it's very common application. So it's already, so Mathematica here has already built the architecture, has already trained it. Now, when the first time I run this thing, it's going to actually access by internet to the pre-trained model. So you need to have some kind of account. It's free, by the way, to access models in the repository. It's free. You just have to sign up, and then it's going to download that and run it. Okay? Now, what else can you do with this picture? Let's try something. This thing is called image convolve. Yeah? Image convolve. What does image convolve do? Yeah, image convolve do. What it does is very simple. You take the picture, right? You look at the cell. Okay, you look at the cell in the middle. Now, in this case, the convolution filter. Convolution filter. Yeah, remember that name from the on the exam. The convolution filter in this case is a matrix of size 3 by 3. Yeah. Now, it will make more sense to do black and white picture, but for now, let's just play with it. What it does is it puts this array of 3 by 3 on top of the individual pixel. Yeah. So let me try using this. I think right on this is much clearer. So let me do that. So if I zoom in, right? If I zoom in, each individual picture is going to be made up of individual pixels, correct? Yeah. Well, that's not good. Never mind. We'll go back to the old way. It's not very good. Guys, last Friday, went to lecture at Sunset and used that. It's a lot of creative. Everybody can see. And long side of it, right over. I'll move on. Anyway, okay. Imagine it's black and white. Okay, it's black and white. So it's number between 0 and 1. Yeah. Let's say I put some, just make it something like 0, 0.1, 0.7, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.9. Yeah. Can you guys see it? That's not better, is it? I'm trying to see if this is better. That's not better. Okay. Okay, let's go back over here. Okay. So all this pixel, right? That's all individual number. 0.5, 0.1, 0.2, 0.3, whatever. Okay? That's image intensity, right? So what is 0? 0 is white. Oh, sorry, black. 1 is white. Okay? And everything else is gray. Okay? Imagine working in a gray scale. Now, what happens is this. I'm going to create another picture, right? From the original picture. The way I'm going to do this is I'm going to apply this kind of 3x3 filter. Yeah, what? I'm going to put the 3x3 filter. Guys, look. I'm going to put the 3x3 filter here, right? On top of this. And I'm going to multiply element by element. Yeah. So whatever value is here, it's going to be multiplied by this value multiplied by that, this value multiplied by that, this by that, this by that, this by that, by that, by that, by that. So element-wise multiplication. Whatever I get, I put it here. And whatever value I get, I put it here. Guys, don't talk about yourself. Guys, that'll do. Not just that. Okay? Next, I'm going to move this thing one step. Okay? And whatever is over here, multiply 1 by 1, 1 by 1, 1 by 1, and I put it over there. Okay? Then I move over here, multiply. Yeah? So what am I doing? What I'm doing is I'm replacing individual cell by combination of the cell itself and its surrounding. Yeah? What I'm doing is multiplying the cell by itself and its surrounding. Yeah? And then create a new cell. Good. Very good point. If you notice, and he noticed, if I get this, right? Everybody look up right now. Yeah. What your friend was saying is that when I apply this, it only works for this thing, right? That has the middle and the surrounding. What happens to the edge? Well, the edge gets left out because you get this thing here. Right? So if I did this, and the original was 5 by 20, let's say. 5 by 20. Picture. Yeah, 5 by 20. And I did this technique. What happened is it's going to fit down 1 pixel. It's going to get down to 4 by 19, correct? That's not so bad. It's 1 pixel at the end, right? But this is a very good point what that you raised. What if I want to make this convolution process 5 by 5? That means the first step I can apply to is here, right? So I'm losing 2 at both sides, right? Okay. So this is where the technique, I guess it's a heuristic. The heuristic is to do what's called padding. So maybe take the value of this, right? You want to do basically convolution on that. But there's nothing here. So you pad it. Okay, you pad it, you put some value in here. Okay, now you can say, well, it would make more sense to put something like 3 over here, 1 over here, 5 here, or maybe you put all 0 or some kind of average. But this is called padding. Okay, So you have the original picture, so that when you find a convolution, you end up with the same dimension. Yeah, that's called pattern, right? Called pattern. That is to make up for the fact that, yeah, you have this kind of edge effect, right? Now, that's not all that critical to our focus. But the focus we want to do, I want to focus is that this convolution, like a neural network, has specification, has two-stage specification. One is the architecture, one is the weight. Okay? In this case, the architecture is very simple. It's square. So you only specify 3 by 3, 5 by 5, 4 by 4, 6 by 6, 7 by 7. Okay? So this is sort of like the size. Once you specify the size, you have to specify what to put in there, right? That's equivalent to the weight. Yeah. So what is the number I'm going to put in here? What can I put in here? Now, brings that thought. Go back 20, 30 years. Image processing technology at that time used something like this. Okay? It's called digital image processing. But they literally define, they don't use the training, they define what number you put there. And based on certain patterns, you get different effects. Yeah. In order to show you that, it's very easy. Let's go to Wikipedia page, I think. There's a Wikipedia page somewhere that I opened. This thing, okay, this thing that we will call convolution filter for our class, in the old days, in the image processing, nothing to do with neural network, that pre-neural network, let's say. It was called something like a kernel, like a image processing kernel. So if I apply this, what happens? I'm taking the middle value multiplied by 1. I'm taking the surrounding value and multiplied by 0 and adding. So what happens? Nothing happens. Right? Nothing happens. That's why it's called identity. So you multiply 0 to that and multiply 1 to this 0.9 here. So you get what? You get 0.9. You basically copy. Okay, so nothing is different. Now, if I apply this, I get all kinds of interesting patterns. This is called edge detection. The reason it's called edge detection, let's focus on the bottom one. It multiplies whatever the cell is looking at, the pixel by a high value. And surrounding suppresses. Right? So if they're basically sharpened very much the contrast. So it's going to basically, what's in the middle, get raised up. Everything else, if it's lower, go down, right? And you can do all kinds of stuff. Now, the opposite of edge detection is blurring. What is blurring? Blurring is when the picture is not fuzzy, right? The reason the picture is fuzzy is like, you have, 28 by 28, but it looks like 4 by 4 pixels. That's because the values are shared. So the way to blur is basically to share the values. So if you take all the surroundings and add them all up, you blur. And so this would be something like the blurring. Box blur. Now the reason this is called box blur is to say it takes equal weight, right? It's 3 by 3, so it's 9 cells. You take 1, divide by 9, 1 by 9, 1 by 9, 1 by 9, 1 by 9. So this blurs the picture of that little rectangle, right? So whatever the value of pixel here is average, it's kind of average. It's kind of average. Okay. Now, I can tell you what happened. When I was doing starting my Ph.D., I was in a applied science system. I was working on financial problems. My friends were working on medical problems, looking at picture of heart and brain and whatnot. And they were just doing signal processing. And in those days, this is how machine learning work? You apply well-known kernel. You apply well-known kernel picture. You get some kind of information like the end, blah, blah, and then you learn to recognize them. Okay? So in other words, this thing is not learned by the machine. This thing is fixed by scientists. Okay? Use some kind of well-known technique to filter, maybe sharpen the picture, edge detect, or blur, or something like that. Use that as information to do object recognition. It wasn't successful. It was not very successful. Okay? So apply the filter first to get some information and extract from the picture, and then use that to create a neural network to detect objects. That was sort of like the intuitive vision of obvious things to do, right? Including the image processing kernel, which is well understood, with NLP, which is well understood, putting them together. Right? So you can think of that as a stage one of object recognition. Yeah. So we have multi-layer perceptron from last lecture. Yeah. We have image processing kernel from way back when. So let's say in the 80s, you put image processing kernel to extract some information. Use that information to feed to the NLP and try to learn what it is. Yeah. It turns out that didn't work. The breakthrough that we have today, the breakthrough has enabled this very, what we call it, simple power. It's really, it's right there. We almost got it. Basically, instead of using the predefined image processing kernel, you make the values here learnable, as if it were a neural network, and then you train it. That is the success of today, what we call convolutional neural. Say that again. Yeah. So if I have an image, it has so much information, and we want to do that kind of extracted information. So you pass this through some kind of digital processing kernel, and you get some kind of representation, and you put. Okay, next class was steal from my room. You put it in FLP and do some kind of object recognition, cat or dog. Yeah. This didn't work. Okay, I was there. This is kind of like this is very difficult, but this was a standard style. You do some kind of something to get the gear. This is kind of numerical. This is image. Get to some processing, get to number, put it in MLP, and then object recognition. We did something else as well. For example, wine tasting. Wine. People make a big fuss about being able to recognize wine from different regions, right? So they put a cup of wine here. Okay. Use the chemical sensor, right? Once the chemical sensor outputs into some kind of cable, and then you try to put it into MLP and try to learn whether or not this is from the Lower Valley or this is from the Chateau or blah blah blah. Okay? So everything at that time was done this way. Basically, the neural network starts here. Yeah? This is something you might not get in any ordinary textbook. This is where the neural network was. Everything else was pre-processing. It's reminiscent of statistics analysis, where you can't do anything with statistics unless you deal with numbers. Right? It could be nominal, ordinal, interval, scale, but it has to be a number. It can't be boy or girl. It has to be 0 or 1. So you have to convert to the number first before you start doing statistics. I don't know if you've got same kind of approach. You have to turn everything into this number, then you feed the neural network. Okay? Then you feed the neural network. So it doesn't matter, chemical, whatever. Okay? Now, some of that still works today. Some of that still works today. This kind of pre-processing. For example, we have a project that's trying to detect this other be pre-processing using spectral analysis. Yeah, spectral analysis. But the point is that this was the way neural network started to be applied. So they're like substitute the artificial neural network NLP went to do statistics. Yeah, start from number and end up with the object you want to learn. Okay, that didn't work. Now, what happened with convolutional neural network is this. This digital processing kernel, which we now call convolutional filter, right? Filter. A filter is a fixed thing. It has a fixed number like this. But now, instead of calling a filter, I call it convolutional layer of processing. This thing contains this thing, but the value is not fixed. The value is learned like other neural networks. You add this together, you get the breakthrough that eventually ends up. Because the machine is not just learning from numbers to classification, it's actually learning how best to extract information from it. It's learning the convolution, it's learning the filter. Yeah? So you can think of it as learning the mapping, and learning also before you learn the mapping, you learn the filter. You learn the So it's not going to end up with something like this. If they end up with some number like you know, it's not going to be symmetric. 1, 1, 2, 4, 4, 1. It's going to be some way. Okay, that's learned by neural network. It's going to be very messy. That is basically how we came to today. And it's like looking back, saying, "Well, we almost got it. We almost got it. We were so close. We used NLP. We went backwards a little bit, one more step, and make the number here trainable or learnable from the data. We would have achieved that breakthrough." Okay. Now, so that leads to our thing today. Now, before I do that, let's try a little bit more. You can see that this here is predefined, right? So it has basically edge detection, sharpening, and blur, and blah blah blah. So this is traditional. So let's go back to our new share and go back to Mathematica. If I did this, okay, if I did this, okay, just like that picture. Remember the bottom was what? 8 in the middle, and then -1 all around, right? Okay, let's try what Wikipedia show with your picture. See? Okay. So it's doing the edge detection. Yeah. But I guess it's a little bit dark. Actually, Mathematica, if all you wanted to do, okay, not to do anything further, if all you wanted to do is edge detection, it's better to use Mathematica's built-in function called edge detect. Okay? So that's you guys. Okay. So that's a picture that we took, right? And you recognize it now. Now, this, by the way, helps a little bit explain why it didn't pick up other things. It's very hard to pick up something tiny like this, you know, but it picks up this, it picks up this, it picked up this. Now, let's try, just for fun, some other value. So let's say just to show you how sensitive this thing is, instead of doing the both, I just put 0 here. Get something else entirely different, right? It kind of does this kind of sharpening. Take the middle and compress the nearby. That's what it does. Take the middle, compress the nearby, and it seems to work as some kind of sharpening. So you can see that it's very what they were doing. They were using 3D sign filter to extract information from the picture. But you can see that this 550, this is 0, this 4 number completely changes the output. So that's why convolutional neural network is so successful, because it's so hard to define the value for that convolution. It's better to let the machine choose or calibrate the function. Okay. So we come to this thing called convolutional neural network. And we can go to a nice representation of that picture with, by the way, you can play around with this and all that, but so no, okay, we're gonna leave your friends here, right? We're not gonna look at that picture anymore. Okay. But again, this is built in. So let me go back to here. What's today? Second. Now, let's go to this. So let's look up the word convolutional neural network. Wikipedia has nice picture. I don't want the explanation because I can do that. I want the picture. No, not nice. Let's find another picture. I think this picture is good. Oops. Sorry. Okay, this is a nice picture. Right. So what happened is, this is the original picture. It's basically a grid of values. Now, remember I told you that we have black and white screen and how do we deal with color screen? In black and white screen, for example, the number of digit recognition, we have a 28 pixel by 28 pixel, right? But if you have color, it will be red, blue, and green. So it's intensity, not of light. Okay, from 0, black, 1 to white, it will be something like 0, black, 1, red. And if you have another layer to that, which means 0, black, 1, blue, and anything else is dark blue. And we have 0, black, 1 being green, and everything else being dark green. But when you add it all up, and brightens it, okay? So when you look at it, you look finding red, blue, and green. But when you analyze, it's actually 3 different numbers. So that's why if this looks like a matrix, yeah, 28 by 28, you have the third index. They refer to what the mathematician and physicists call tensor. That's why you start to hear the word tensor. Okay? Tensor. Yeah? Tensor is a mathematical object that requires 3 indexes or more. So you can have 4 tensors. Okay? In this case, a screen is called, a color screen is called a 3 tensor. Okay? Because it requires 3 indexes. Now, technically speaking, even if this has 1 index, it's also called 1 tensor. Yeah. So you can say that 1 tensor, a scalar is called 1 tensor. Yeah. Sorry, a vector is 1 tensor, a matrix is 2 tensor, and 28 by 28 by 3 is a 3 tensor. That is the kind of tensor you most need. will be familiar with, because the application, you want to apply this using the library from TensorFlow, made available free, which you guys can play. Most of the time, that kind of tensor is free tensor. So they don't call it free tensor. But in theory, you can define 4 tensor, 5 tensor. But 3 tensor is basically the word common. This is all you need, right? You need a speed, height, width, and the depth is the color. Okay. So now, if you look at it this way, you can see the 2 parts that I was talking about earlier. This part here that has all the red and green guys, the red and green here is basically our NLP. The red and green is our NLP. And this here is all the learning convolutional filter. Now, if you read carefully, it has other words as well. Words like math tooling, something like maybe there's video research, word like normalization, never mind that. This is kind of enhanced. The point is that this NLP here, this fully connected neural network here, is the original inspiration from the brain, cellular brain. NLP and blah, 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 blah. This one is sort of like, well, you can think of it 2 ways. You can think of it as taking traditional digital feature, digital processing feature, digital processing kernel, digital processing filter, and make it behave like a neural network. You can think of it that way. In fact, originally I thought this is how they invented it. Because after all, in my lab, we have NLP and we have digital filter. So I thought that CNN was about converting this into a learnable. Yeah, I thought that was the approach. It turns out the story is more interesting. Yeah? And I'm going to give you a 2-minute talk on where the convolutional neural network comes from. And let me go to never mind. Let's do this. Fukushima. You guys know, Fukushima, the nuclear accident? Well, that's the name of the town, right? But Japanese people like to use that as their last name as well. So this guy, by the way, who came to Thailand, I met him, very nice. This guy. I'm trying to find his picture. Kunihiko Fukushima. I should have a picture of him. Where's the picture? Oh, no picture. Sorry, guys. Anyway, long story short. And this is very interesting because a neural network is now used to recognize picture of cat, right? Actually, it starts with cat. Literally starts with cat. This guy, in 1959, who built the user? Right? Good cat here, like that here, and then good electrode in different parts of the cat's brain to see how the cat's brain gets excited. Right? And then they show picture of various things, like simple things. An edge going sideways, this way, circle, all kinds of stuff, from simple to complex. Okay? And look at the cat's brain. Look at the cat's brain. It turns out what the cat did is this, very interesting. The first layer of the brain that has to do with visual stimuli recognizes, right? Recognizes basic things. But here's the interesting thing. You can imagine that they varied the experiment. Sometimes time, not only do they change shape, they change position. So they put the thing here, that's one picture. Maybe another picture like this. Same shape, different shape. See, if you think about it, the biometric facial recognition is very easy. Because when you want to scan, you want to like see the face here, you move the door, you actually align the face, right? The eye to be here, the eye to be here, the nose to be here, the mouth to be here. So you have to have that, I was talking about it. Because you literally force the picture to be like this. Okay? So you can measure the ratio between the width of the eye, the nose, blah, 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 right? But you can't do that. When you recognize your friend, you don't go up to the face, oh, hello, I know who you are. You recognize the friend from afar. So it doesn't matter if your friend here, there, yeah. It's called position invariant. Invariant means it doesn't matter. Nowadays, we have other words as well called expression invariant. If your friend is smiling and your friend is unhappy, you should be able to recognize that same person. That's what we can do nowadays. AI can do that. Also, if your friend comes in the dark, comes in when it's very lit, the sunlight, or illumination. So cause, illumination, expression invariant. But back in 1959, the recognition that actual position invariant was a big deal. It was a big deal. Because what happened is this. When the cat sees this, part of the visual neuron get excited. Not all. Not all. When this picture happens, maybe another part gets excited, but not all. But how can they become happy to recognize both of that? When this excites me, some neuron, this excites another neuron. Well, there's another layer of neuron that doesn't care where the decision is. It's position intensity and this takes all of it. So you can imagine, I think it's called S cell and C cell detail. S cell is sort of like, oh yeah, some S cells is, yes, there's a shape. Yes, there's a shape. And C cell, C cell, round up the information in action of that. It's sort of like saying, okay, oh, you see an X, doesn't matter where you are, it is an X. This, by the way, is how Professor Fukushima in 1980, so this is even before my time, started to do this he didn't call it that, he called it neocognition. Okay? So basically, he's mimicking, he figures that part out. But it has to wait until about 1990 when Professor LeCun kind of like put this architecture in the form of today, where you have the kind of convolutional NLP connection. Yeah. So there's a lot of breakthrough. Okay? So let me go back. What's important is the NLP. That's the neural learning. The idea that you have a model of a neuron replicated as artificial neuron receptor layers and created this nonlinear function that we talked about last time. That was milestone number one. Milestone number two, which actually occurs around the same time, was the recognition that acts on this kind of neural process. So you can imagine that the first layer is like convolutional layer. The second layer is a natural layer. I'm being very loose. Okay, but this is the inspiration also from the brain. But not from individual neurons, but from looking at cat layer of excitation. Okay? The receptor would be something like you take a single neuron from the raw and you do electrical signal and you get a signal wire. You can analyze the function of the neuron. This is kind of analyzing a function of the visual neuron. Okay? So you have NLP, We have an experiment of Google in 1959, inspired real pop. So now the architecture comes together in the late 90s. Yeah, late 90s. When you put that together, you say that's another milestone together. But the real milestone that happened in 2010, what happened in 2010? Well, what happened is people start to play graphic game, computer graphics. What happened is this kind of neocognitron, this kind of thing. Okay. It's not just a few layers. Remember last class we talked about multi-layer perceptron, and I said a multi-layer perceptron is beginning of building, right? You want 3-story building, 5-story building, 10-story building. Well, when you get to something like this, where you have convolutional layers in front, you can think of this as other type of layers. Except you end up with so many layers. You can have 20 layers, 30 layers, 50 layers. Yeah? And you have so many parameters. So many parameters that the computer using CPU alone cannot solve. The breakthrough milestone number 3 or 4 is when some computer scientists decided to use gamers GPU parts from NVIDIA. Okay? Parts that are designed to draw a picture of Ninja Warrior or whatever it is. Okay? Use that to do this multiplication. And the breakthrough that came, I don't remember exactly the search. You can say something like, how long did it take to train the original Lynette? Okay. So Jan LeCun here in 1998 put it together, and the original training. By the way, his project was he was I might be wrong, but I think he was passed as a consultant before model. In America, he used like a zip code and it's handwritten, so they want to recognize the numbers in automatic sort. And that's how the MNIST data came about. So this was the thing here. LeCun, and so that was Lynette, AlexNet. Okay. The breakthrough in AlexNet was 6 days. Okay, guys, that's historical. AlexNet is the milestone that I'm talking about. Okay, the same the Lynette is the architecture by doing here, but like it's 90 epoch. Epoch is like a rocket trading. For 6 days. 6 days using NVIDIA GeForce GTX 580. Yeah. It takes 6 days to do that. Now, not to belabor the point, but today we're going to do this. Have we done this? We haven't, right? Okay. We're going to repeat what was done, kind of like in the AlexNet. Okay. So never mind this. This is my data. Okay. I download this data. Okay. This is basically the MNIST data that was created for the problem solved from the post office. You write that number. This is a pixel. This is not a number. This is a pixel. Okay. This is 28 by 28, right? And it's the target is to say this picture is number 9. That's the objective. The objective here is this number should be number 4. You guys see that? So what's happening? You have 28 by 28 by 1, because it's black and white, values between 0 and 1. Now, in the middle of the black, that would be 0, but it's all white and 1, and everything else in between. The convolutional layer, sort of like that's the thing that we talked about. Yeah. And then the cooling layer and all this, and then now the layer fully connected. And try to learn. This is a 9. This is a 4. This is a 0. So this is just a random sample of 5 items. Now, what I'm going to do is I'm going to import the architecture. Again, I just go to neural net. When I click import net model in net, it imports an architecture. Meaning what? This is like taking the building plan, but it hasn't been parameterized. What you said, I want to build a 5-story apartment. So you download the plan, but that plan allows you to what? To move like the width of the room, the height of the ceiling, the size of the window, blah blah blah. CDE, right? So those are free parameters. Those are weights. Those haven't been specified. You have text over the width and the length and the height of the ceiling, but whatever it is, you can do your preference. So you have this. And this is where you see. The first layer is called convolutional layer. Okay. Just ignore this. But basically, down here, this linear layer and RAM here, this is equivalent to my NLP earlier. So you can say this is sort of like convolutional layers. This is the image processing layer. Down here is the object recognition layer. Okay. Now, it says it's uninitialized. It's uninitialized, right? So we have to train it. We have to train it. Okay? We have to train it. Now, this is where I'm going to train it. Now, I put timing here. Let me get rid of some of this so you don't get confused. Okay, ready? Don't go yet. Don't go yet. And we're going. Okay. Timing is just to tell me what the time is. This is my raw architecture. This is my raw architecture. I'm going to train it using the function called netTrain. Train the architecture using this data set. Okay, ignore this thing. This is called validation set. We'll talk about that later. But I'm going to do what Alex, the creator of AlexNet did, which is to use my GPU. Except my GPU is a little bit more expensive. I think it's 1070 or something. Okay, it's not that expensive. It's still a laptop GPU. Remember, originally it took 6 days. Okay, so let's wait for 6 days or less. Yeah, it's starting. This is the error function. It's going down, it's going down, it's going down, it's going down, it's going down. Right? Yeah. So this is basically what the AlexNet architecture and LeNet might be slightly different, but just to give you an idea. Okay? So this was something that in 2010 or maybe 2000 days. But it was worth it because when they published this paper, they became world famous. So they had the insight to use the game card, basically. You can say that. So they have multi-layer-centron as a neural learning. You have the neo-opticon, that's a sort of like convolutional inside. Put them together, good bit. But then, not only that, you use that will do 6 days. Okay? doing that now. So hopefully it's going to take minutes rather than days. Okay. If you want to go to now. Let's go to pilot. This blue line, by the way, is called validation. What happens is that the neural network is trying to learn as much as it can. But the neural network can also get smart and memorize all the time. So while it's learning, the algorithm says, I'm going to set off another part of the data and test on it. You cannot train on it. You cannot train on it, but I'm going to do that part of it. So I use my data to train. Every once in a while, I use that to test against the next step. That's the rule. What's going to happen is that the training gets lower and lower. Training error, lower and lower. Okay. Now, the reason it does this is because it's still having an algorithm. But periodically, we test against a data set. So the error is going to be higher. And but it's going to get lower as well. At some point, it's going to be better. In other words, the training error goes down, but it's starting to be a little bit more. So when you perform against the 10% set aside, that's what it is. So the generic curve is okay. This data set is not used to train the neural network because the way that's adjusted on it. But it's used to indicate where to stop. Now, to stop backwards, in other words, to allow this thing to go forever, it's inspired, but you know that this is learning noise. So you come back, that's what it's done. And it's done. And instead of 6 days or days, it took what? 149 seconds. Okay? So about 2 minutes and a bit. So it took 2 minutes, 3 minutes, let's say, to do what 10 or 20 years, 10 years ago. Yeah, so we have done a lot. And that's the reason why now let's see if this model works. Okay. Now to test this, you have to test against the data set that's set aside from the beginning. It's called test set. So this is my test set. Okay, this is my test set. The ground truth said this is 5, this is 7, this is 1. So let's see if I apply it, I get that. 5, 7, 1, 5, 4. So it's correct. Perfectly correct. But sometimes it's not correct. So we can try, you know. Now, obviously, classification, you can say, what's the accuracy? Yeah, the accuracy is, so this is not just measuring just 5 sample, but everything. Let's see how big. So, dimension, length of train. So we have 60,000 handwritten digits to train. Okay? And we have 10,000 pictures to test. Based on those 10,000, the accuracy is 99.45%. Now, it's good. Is it good enough for you to know that the accuracy of that data is 99.45%? Well, yeah, it's good enough to say that. But we would like to know a little bit more because this classification is not a binary. It's not a yes no, right? And remember, binary, it does not matter whether or not all combinations are right? So in this case, because you don't have binary, you have 10 classes. So that is what's called confusion table class. Now, for those of you doing confused classification problem, I expect to see confusion tables as part of the form. Now, in this case, how do you read this? You say that if the actual class is number 0, it identifies 0. Okay? So how many 0 are there? 980. Let me make it bigger. Can you guys see it? Okay. Actual, predicted. Actually, there are 980 0. I correctly predict 972 of them. One of them I predicted as 1. That's an error. I predict 1 as 2. I predict 4 as 6. I predict 2 as 7. So that's an error. But mainly the diagonal is very good. The perfect model, of course, would have all just the diagonal. Yeah, so that's yeah. Now, I did this same slide in front of you just to show you the level of problem that it takes about 2 minutes. But because this Lynette is a known problem, they've done it for 1,000 times, like a picture, presentation, and multiplication. So obviously, it's already been done. So if you don't want to retrain, okay, you can just download the whole model. This is it. Instead of download just Lynette, remember originally I did this, right? I just download the Lynette and train it. Now I download a train Lynette. So this is a Lynette train on every data. Now, the difference is once I do this, it's got the same architecture as before, but now it doesn't say visualize. The symbol is the same as color. Yeah? Remember when I originally imported just the architecture? It looks like this, but it says uninitialized, right? Uninitialized, meaning the weight is just empty, right? Yeah. You can randomize, but it's not trained. This one is trained, and you can do the same thing. Now, it obviously has as much accuracy. Okay. So obviously, it's going to have very high accuracy. Yeah. Now, based on randomness, it may not be exactly the same. So that's that. So, what was demonstrated is that today, there are different approaches to using pre-configured models. One, you take the architecture and retrain it. So in this case, you use that and retrain on your data or a new set of data. But if the model is going to be used for the same kind of data as we have already trained, you might as well copy the whole thing, right? Download the whole thing. This is another example. This is basically this thing where you take the same architecture, but you train against different data sets. Okay, this data set is a big object recognition. The first one is 0, designated feature, 8, designated handbag, and so forth. Okay? So implicitly, by the way, this kind of thing is what was behind the object context function. Okay? So that one is a lot more complete. So in the old days, maybe in Mathematica, much earlier version, we would have something like this, but we wouldn't have object context function. Okay? But the application became more and more ubiquitous. So in later versions, they add that. So it does this thing for you. Look at the picture, scan for objects, look rectangle around it, give you the label, but the thing is what it is, gives you confidence. And so you can use that and they copy. So in earlier versions, maybe it wasn't, you can do the same thing. You can do the same thing, but it's not one program. Like I said, what Mathematica does is as it explores the functionality and application, it say, what is the more usual type of analysis? Okay. So that single function here, this object contents. So if you think about it, this thing, Linus, is maybe 10 years old. So they package it into this, package it into this thing where you can literally recognize objects. So you can think of from column 1 to column 2 as a similar problem, right? Except in this case, it's much harder. It's not 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's feature object. And how many kind of objects in the library that you recognize? Okay? I don't know. You need to look up the package. So maybe it has predefined 10,000 types of objects. How to class, to pencil, to paper, to table, to cursor, to dog, cat, etc. So this is a lot more clever. It's a lot more clever. Okay. Person. Now, what's so good about this is it doesn't give you overlapping classification. But notice this. Notice this guy. This is a person, right? See him? But here, this is also subcrop down here as handbag. All right? Right? In fact, you get a lot of that. So for the project, we can say a girl selling a handbag. She's not going to sell handbags like this. She's going to sell handbags like this. So there'll be a bigger problem say a girl. There'll be a subproblem say handbag. Yeah, that's automatic. Okay. So this is CNN. Yeah, this is CNN. I'm going to send you a link to this YouTube. Okay, that covers CNN in an animated way. Now, in their example, they use this 2x2 picture, but it gives you a very clear understanding. So, do we need to take a break? Do we need to take a break or not? Okay. All right. So let's take a 5-10 minutes break. 10-minute break. Pick up.